Welcome to the fifth session of this differentiation series. In this session, we will continue to demonstrate how to use algebra techniques to evaluate limits and gradients of composite functions. In addition, we will explore the relation between functions and their derivatives through 9 worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the series of differentiation, and this is the fifth session of this series. Here, example 1 is to evaluate the limit of f of x naught plus n delta x minus f of x naught minus n delta x all over delta x as delta x approaches 0, given that f of x is differentiable and f prime of x equals a constant c at the point of x naught. To evaluate the limit, the first principle is applied here to find the value of the limit as delta x approaches 0. On the numerator, the term f of x naught is subtracted and added as shown in red. According to the limit properties, the limit is written to m times the limit of f of x naught plus m delta x minus f of x naught all over m delta x as delta x approaches 0 plus n times the limit of f of x naught minus n delta x minus f of x naught all over negative n delta x as delta x approaches 0, which equals m times f prime of x naught plus n times f prime of x naught, which can be further simplified to m plus n or in parentheses times f prime of x naught. Hence, the limit equals the m plus n or in parentheses times c. Example 2 is to find the value of k given that the limit expression equals f prime of x naught over 3. According to the first principle, the derivative of f of x at the point x naught is written to the limit of f of x naught plus delta x minus f of x naught all over delta x as delta x approaches 0, which can be arranged to k times the limit of f of x naught plus k delta x minus f of x naught all over k delta x as delta x approaches 0, which can be further simplified to k f prime of x naught. Since k f prime of x naught equals f prime of x naught over 3, k equals 1/3. Example 3 is to evaluate the derivative of f of x at the point 1 over 2, given that the differentiation of f of 1 over x squared equals 1 over x. According to the chain rule, the derivative of f of 1 over x squared is expressed to f prime of 1 over x squared times negative 2 over x cubed, which equals to 1 over x. Hence, f prime of 1 over x squared equals negative x squared over 2. After substituting x by square root 2, f prime of 1 over 2 equals negative 1. The criteria in example 3 are that f of x plus 1 equals a f of x. The derivative of f of x at the point x equals 0 equals b, where both a and b are non-zero constants. The question is to evaluate the derivative of f of x at the point x equals 1. According to the first principle, the derivative of f of x at the point x equals 0 equals the limit of f of x minus f of 0 all over x minus 0 as x approaches 0. which equals b. Since f of x equals f of x plus 1 over a, f of 0 equals f of 1 over a. Hence, b equals the limit of f of x plus 1 over a minus f of 1 over a all over x as x approaches 0, which is simplified to 1 over a times the limit of f of x plus 1 minus f of 1 all over x as x approaches 0, which equals f prime of x over a at the point x equals 1. Hence, the derivative of f of x at the point x is 1 equals the product of a and b. The given criteria in example 5 are that the function f of x is differentiable in real number. The question is to ask the following statements are true or false. The statement A says if the limit of a function f of x will approach negative infinite as x approaches negative infinite, when the limit of its derivative would approach negative infinite as x approaches negative infinite. To prove the statement is false, what we need to do is to find a counter example. For instance, we assume f of x equals x. In this case, the derivative of f of x equals 1, while the limit of f of x approaches negative infinite as x approaches negative infinite. So the statement of A is false. The statement B says that if the limit of f prime of x will approach negative infinite as x approaches negative infinite, and then the limit of f of x will approach negative infinite as x approaches negative infinite. The counterexample disapproves this statement is that we assume f prime of x equals x. Accordingly, f of x equals 1 over 2 times x squared plus c, where c is a constant. So the limit of f of x approaches positive infinite as x approaches negative infinite. So the statement of B is false. Here we continue to work on the statements C and D of example 5. The statement C says that if the limit of a function f of x will approach infinite as x approaches negative infinite, then the limit of its derivative would approach infinite as x approaches infinite. In this case, there is a function f of x equals x, which is used as a counterexample here to prove the statement is false. Based on the assumed function f prime of x equals 1, no matter what value of x it takes, therefore the statement of C is false. In order to prove the statement D, we need to use the method of contradiction. Here we assume when the limit of f prime of x approaches infinite as x approaches infinite, the limit of f of x equals a constant k as x approaches infinite. Then we apply the Lagrange theorem on the interval between x and x plus 1. Accordingly, f of x plus 1 minus f of x equals f prime of Cauchy, where Cauchy is between x and x plus 1. Since the limit of f of x plus 1 equals the limit of f of x equals the constant k as x approaches infinite, and f prime of Cauchy equals f of x plus 1 minus f of x, which equals k minus k, which is 0. Back to our assumption that f prime of Cauchy should be approached to infinite. So the result is contradictory to our early assumption. Therefore, the statement D is true. Example 6 is to find the derivative of the function y equals natural logarithm of cosine 10 plus 3x squared. initial observation tells us that we need to apply chain rule to find out the derivative of this composite function. Since we have already learned that the derivative of natural logarithm function is the reciprocal of the function times the derivative of its inside function, and the derivative of cosine function is the negative sine function times the derivative of its inside function 10 plus 3x squared. Hence, y prime equals the reciprocal of cosine 10 plus 3x squared times the derivative of cosine 10 plus 3x squared, which equals the reciprocal of cosine 10 plus 3x squared times negative sine 10 plus 3x squared times the derivative of 10 plus 3x squared. After being simplified, the derivative of the function becomes negative 6x times tangent 10 plus 3x squared. Example 7 is to find the derivative of the function f of x equals 5 over the square of 2x plus 2 cosine x. To find the derivative of this function, the power and the trigonometry rules are applied. Since f of x can be written to 5 over 8 times x raised to the negative 3 plus 2 cosine x, its derivative f prime of x equals negative 15 over 8 times x raised to the negative 4th minus 2 sine x, which is simplified to negative 15 over the product of 8 and x raised to the 4th minus 2 sine x. Example 8 is to find the derivative function of f of x, given that f of x is differentiable and it equals the fraction of x plus 1 all over the sum of x and 2 times 2x minus 5 all in parentheses. Before working on its derivative, we need to transform and simplify the function body first. Accordingly, f of x is written to the fraction of x plus 2 minus 1 all over the sum of x and 2 times 2x plus 4 minus 9 all in parentheses, which is simplified to 1 minus the reciprocal of x plus 2 all in parentheses times open bracket 2 times x plus 2 all in parentheses minus 9 close bracket. After expanding by multiplying them out, it equals 2 times x plus 2 all in parentheses minus 9 minus the fraction of 2 times x plus 2 all in parentheses minus 9 all over the sum of x and 2, which is simplified to 2x minus 7 plus 9 all over the sum of x and 2. Hence, its derivative function equals 2 minus 9 over the square of x plus 2. Example 9 is to find the derivative function of f of x, given that f of x is differentiable and it equals open bracket x squared minus x minus 3 all over the sum of x squared and 1 close bracket multiplied by x squared plus x plus 1 all in parentheses. Similar to the previous example, f of x is transformed and simplified before working on its derivative. Now, f of x is written to open bracket x squared minus x minus 3 all over the sum of x squared and 1 close bracket times x squared plus 1 plus x all in parentheses. After being expanded, it becomes x squared minus x minus 3 plus x times x squared minus x minus 3 all in parentheses over the sum of x squared and 1, which can be further simplified to x squared minus 4 minus 4x minus 1 all over the sum of x squared and 1, Up to this stage, we may use the quotient rule to work out its derivative. Hence, f prime of x equals 2x minus the ratio of 4 times x squared plus 1, or in parentheses minus 2x times 4x minus 1, or in parentheses to the square of x squared plus 1, or in parentheses. Therefore, the derivative function f prime of x equals 2 times open bracket x raised to the fifth plus 2x cubed plus 2x squared minus 2 close bracket over x squared plus 1, or in parentheses squared. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.